Hello, my friends. Hello, my RF and microwave design engineers, circuit design, circuit and system design engineers, my fellow graduate students. Welcome all. This is Dr. Mohamed Nezami presenting the last video on this series of designing and 3D modeling of ferrite isolators and circulators. My dear friends, this is the fourth video, as I said, and today we're going to cover a little bit deviation from the what I have covered previously. As you might know, let's turn back to the so this is my channel, YouTube channel, with all the videos in there. You can view them. Please subscribe to my channel so we can increase the traffic on the channel. These are the three videos that I've done so far on, in particularly on the ferrite isolators and circulators. The first video, we basically I overviewed the design principles and the different types of ferrite isolators. And then the second part, I did zoom in onto drop-in surface mount microstrip isolators. You can go back to this video and watch that series, how the principles were aided by illustrating some few examples of 3D EM-based modeling and of designed microstrip circulators. And then I went into the strip line circulators, presented that as well. And today we're gonna basically present to you the connectorized version, which is nothing but a strip line circulator where I took off the wave ports and attached SMA connectors. So basically, just reviewing back, like I said before, these are the four different types of circulators that we are concerned with. We've got the connectorized one, whether it's SMA, N-type, or some other variants of that connector types. These are primarily used in the labs, and sometimes we integrate them into systems, transceiver systems, and power amplifiers. Then we have a waveguide. We haven't covered that. I will cover that in a future video by itself, on itself. But then there's these two that we have covered basically in the previous videos, where basically we did the strip line one, drop-in strip line one, and then the microstrip one. So today let's do this. Since I've designed this previously in the previous video, I'm just going to go ahead, and the difference between this and this is nothing but some mechanical integration of these connectors where they attach to some of the strip lines, okay, and you package it mechanically. And that's really what I'm going to do today. Is we're going to come into this is a circulator here, and this is an isolator terminated in one port, which is basically a circulator terminated internally. And this is here is N-type, and this is SMA type. So basically, I'm going to grab one of these connectors, the SMA female jack bulkhead connector solar cup terminal, okay? And then the, as you know from coaxial line characteristics impedance equation, the characteristics impedance equation of a center pan and outer shield with a Teflon insulator in there. Basically, the equation is the ratio of the diameter of the Teflon over the diameter of the center conductor. That ratio, the logarithmic of that ratio, multiplied by 138 and divided by square root of epsilon r, which is the decay for the insulator, which is in this case most likely is going to be 2.1. Okay, usually the ratio of outer to inner in most of these connectors is like 4. Okay, and basically, so this gets attached with mechanically attached to this with 4 screws, and the center pin gets soldered on the inside. Okay, so you can, these are from the data sheets. You can find about this. And there's also here, we give the cutoff equation for the frequencies that you can pass through this. So last time, I know we did illustrate, I grabbed these from the net, shown an individual did a teardown of a circulator. And basically what we did is we have a Y junction, strip line Y junction sandwiched between two ferrite materials, glued together, sandwiched. And then we attach basically connector to it. That's all there is to an SMA type or connectorized circulators. So in this case, this one here, this is a 50 ohm termination, 50 ohm solder to this junction side. And then the other side is basically mechanically fixed to this port here so that you get the resistor to the ground in there. And that way you can also, it would serve as a heat sink as well. So just showing the details, just to review, we have a Y junction with a disc, metal disc. This is from brass or copper. And then we have this one here is sandwiched between two ferrites. And then we have externally, we have the magnetic bias of the ferrites, which are two tiny magnets, basically with some spacers, which they are just two layers of foam, basically. Okay, and then it gets packaged like this mechanically. Okay, now when you look at this, of course, they made it into a square package, but really it's a hexagon shaped where the ports are spaced at 120 degree apart. But what they do is they bend the connectors backwards so that you can actually have it in this form where it's a square form. Okay, so let's turn to the two designs. So what I did last time is so I took one of the circulators that I designed last time, which is stripline circulator, and it's right here. So let's just go through the dissection of this. And this one here, of course, it was designed, I tuned it a little bit further. So it's designed about 8.75 or 8.75 gigahertz center frequency, okay? And it operates between 9.6 to 8.7, okay? All right, so just to show you that this thing is really working, here is the current density on this, and we can animate and show that the current is really flowing from the input port to the output port only. So as you can see here, where the isolated port, there's nothing in it, okay? All right, okay. So let's just go through the just how I created this model. So we're going to, let's just grab everything and hide it all together and then start one by one. This is the E field by itself. Of course, I got to get rid of that. So let's just get rid of that. Okay. So basically, what we start with, as you know, is from the Bosma equations that I presented back in part 1 and 2 of this series. We have some equations where we derive an equation for the dimensions, the radius and the diameter and the height of the ferrites and the dimensions of a strip line. So basically what we have is we have two ferrite materials, okay, one on top, one on the bottom in here, okay. And let's just show these here. Show these in view, okay. So we have these two ferrite cores that they have a diameter which is computed by the equations that I showed. And there's I lifted the middle, I left a gap, which basically that's where we're going to attach the Y junction, the strip line junction. So let's go to that one. And of course, we have the magnets. We have two magnets that are also externally biasing the thing in here. So these are the magnets. They sit up on top. They stack together like this, okay, at a certain distance to provide the magnetic bias for the ferrite cores. Okay, so we have now, let's go to copper. So we have the strip line junction. So I'm just going to show that. Here it is. Okay, so as you can see now, this is basically the design. This is really the complete design electrically. So we put an input on one side, and then the two other sides will serve as the output and as the isolated port. Okay, so and next what we will do is I had a spacer. This is the spacer made of polyester material basically right now. So let's put that in view. So as you can see now, we have all of these together. So now I have the magnet, top magnet, a little spacer, and at the bottom magnet, a little spacer, and then I have the bottom and the top ferrite material, okay, ferrite disc, and then of course is my the Y junction, the metal junction, okay. That's these guys here. Okay, forgot to show the disc as well, so let's show that. Show it. Okay, so let me, in fact, let's go to these and make the transparency a little bit so we can see the Y junction. Okay, so this is basically what I have. As you can see, again, let's review this. So I have a Y junction, okay, two ferrite discs, okay, and then two spacers isolating the physical magnets, external magnets, okay. This structure here is really nothing but a circulator, a three-port circulator, okay. So what I'm going to do next is we're going to create basically the electrical package, the mechanical package that will hold this thing together, and it's nothing but what you see here. So where I have one ground, the top ground disc here with a hole in it so that the magnet fits in, okay? And then the bottom ground in here the same way. So, okay? So, and let's just now put it all together. Now, what I do next is, of course, attach the ports in here. So let's do that. Okay. Okay. Okay, so what I did is then next we're going to put the signal bias. And what I did is I put the signal, the wave ports on the face of the mechanical package sides, on the hexagon sides that are connected, that are across across from the input, as you can see here. So I have port number 1 here, port number 2 here, port number 3 here, okay, which is there, okay. And I left the other one with an air gap, basically the other side. For right now, this side here and this side, there is no metal shield, okay. But you can imagine now, of course, you got to take this to a mechanical engineer next, and then the mechanical engineer, of course, he will retain all these dimensions, but make it into a realizable, mechanical realizable, manufacturing realizable CNC machined pieces together, or 3D printed, okay. All right, so and then of course this is what we get. This is put the response, and that's what we get as far as the insertion loss is below 0.7 dB all the way across. Okay, so right now that's basically the way this thing is right now is actually a strip line circulator, which can be used as a drop-in device, because all you have to do in this one here is extend these ports outward, and then it would basically gets dropped into a cutout in the board and solder to the actual traces on the board. Okay. Now, so next, what we want to do, we want to make it like this, really, like this one here, where actually we have SMA connectors connected to the ports in here, to the mechanical package. So, and that is basically what we have, what I have right here. So this is basically what I did in here is basically is a 3-port circulator, the same exact circulator in here. The only difference is that in the inside, as you can see in here, I put in a small piece of coaxial line going inward. Okay, so basically here's the inner connector right here. Okay, let's see. Okay, okay, so we have an inner connector in here, as you can see, okay? And then I have an insulator outside, and then of course this is a cap, but this is the outside of the outer shield of the transmission line. Okay, this is all now inserted in, and the basically the inner connector in here gets soldered to the Y junction side in here. So let me show that next. I know it's very busy graph, so let's do the same thing like I did to this design before we go further. This is basically the response. So I was able to tune it to a good region in here, and you can see the insertion loss is actually, we can retain just to work between 0.5 less than 0.5 dB of insertion loss. The current, as you can see in here, is going from 1 to 2 and nothing going to 3. And so if we animate that, you will see how that is done. So basically right now, like I said, so what we have, the current comes in here on the center pin, goes into the Y junction, strip line junction, and leave to this port. Very little goes to that port. Okay, you can see it on top and bottom basically. So this is looking downward on the top side, and this is looking from underneath. As you can see, it's working pretty well. So let's go and hide all these pieces so we can just explain. So like before, let's first of all start with the Y junction. Okay, so we've got these pieces. This is the Y junction, the way I got it right now. It's the same Y junction that I had before. Okay, the only thing I added a little piece so that I can solder the center pin to it. So, and the solder, I did use a solder, which is this one in here. Okay, so these are 3 pieces of solder. I had to include the solder effect as well. So right now what you're seeing in here is basically, I don't know why this one is not okay. So let's make it 0 so we can see it. Okay, so we have 3 pieces of solder, okay, simulating a real solder on there. The Y connectors for the coaxial line are basically this. Let's go inner, inner, inner. you sorry. Now, of course, because of the three-side symmetry of this, all I do when I create this, I only create one part here, and then I would grab it and basically duplicate it. You know, you can go in here and you can go edit and duplicate and around axis. Of course, this is already duplicated. I don't want to do that. And then it would actually do that. And that's what you get in here. You can see it in here. So there is a duplication process where I duplicate 3 times at enough around the z-axis with the 120 degrees apart. Okay, so now what we have here is we have basically the inner connectors of the coaxial connector connecting to this. Now, the connector, this one here, electrically, you only have to do 3 pieces, just the inner connector, the insulator, okay, and then an outer outer shield. Okay, you don't have to do it physically, mechanically, just like this. You know, you just all you need to do just electrically an equivalent of that. And the mechanical engineer, of course, you would show him the parts, and he would have a step model. In fact, you could, if you want to, you could import the step model of the connector itself and physically have an actual true connector model in here. But we don't have to do that. So, all right. So let's do the ferrite materials, both of them. So show. Okay. So what we've got so far, as you can see, is the stacking of a Y junction. And let me get these guys select all. Let me do some transparency so you can see the Y junction, keep seeing the Y junction. Okay, so what we have is the Y junction, the 2 ferrite discs, the inner connector of the connector, okay, the inner piece, and then the solder in there. So if you zoom in on this, okay, you will see that the solder piece is actually modeled in there. And it's what, by the way, if you don't use the solder, what happens is that you will, when you look at this, unless you use a solder model, what happens is the disk in here will be touching the strip line, and it will be only connecting at a single pixel, okay, which would not work electromagnetically. That's another reason why I had to use a model for the actual solder, so that physically, electrically, it has a sufficient, generous cross-section of a connection in there. Okay, so let's go to the coaxial line, and let's get the other parts as well. So what I'm going to do is let's do the outer one. Okay. So right now, again, like I showed you before, the way I created these, I create only one and then repeat it 3 times. So this is the equivalent of the outer shield. And now let's get the insulator in here. Of course, when you create these, I create them as discs, cylindrical discs, and then I subtract to get rid of the inside to make it hollow. So basically, you got to do that as well. Okay, so right now, as you can see, I've got in here. So let's go to the inners and make them all solid so we can see them better. So basically, this is what I have right now. As you can see, is a small piece of coaxial line. The length of this doesn't matter, okay? And the center pin is sticking out this much. You could extend it more, it wouldn't make any difference, okay? All right, so now let's put the rest of it. So let's put the let's see, let's put the magnets, show the magnets in there physically, okay? So basically, here are the magnets on top of the ferrites, okay? And then let's see what else. So, oh, now to excite the coaxial waveguide, transmission line, you have to use put it on the face in here so that it's a TEM mode. And in order to do that, you have to create a disk in here as well. So so what I did is I created three circular disks that are metal, and so basically I capped them. They're basically metal caps for the line in here, so I can put the excitation, and that's what you see in here. Let's show the excitation. So as you can see, you have to excite the transmission line with the TM field in there, okay? And in fact, you can zoom in and show the E field on this. Let's see. Okay, so let's zoom in, or without zooming in, we can. Okay, so you can see the E field TEM mode exciting this port. Okay, and that's how you have to create the excitation of the microwave signal in there. Okay, so let's put the rest of the metal in there. So we're gonna grab, select all and just view it. View show, okay? So now this is the whole assembly turned together. So all it is we have some spacers between the magnet and the top and bottom grounds. Okay, and then we have, of course, the air, the vacuum in there to solve for the E field on the inside. Okay, and you can see the again, you can see the signal propagating in there. So that's it, ladies and gentlemen, for this. You know, that way we have covered these three types of Ferrite circulators and isolators. Now, so we started with few equations that were derived in the 1960s for the E field in this cavity that is made of magnets and ferrite material and Y-junction metal strip-line Y-junction, and then we came up with dimensions. Now, I forgot to mention one thing. You realize that this here, I really did not optimize. This is exactly as I derived it, the same dimensions. I did not do anything. So, in fact, right now, all the parameters, it is parameterized using variables. So what I could do is you could come in and start tuning. You could grab any of these components and start tuning them, okay? So for instance, let's see how much time it takes. Let's see the radius of the ferrite. So let me grab that and sweep it with the tuning. So right now it's sitting at 3 millimeters, but let's take it from 2.5 to say 3.5 by 0.1 millimeters. And so we can do that. And then what I could do is I can go in and optimization and do the tuning. So here's the tune. So we're going to solve it and watch it, see what it does. It probably will take a lot of time to finish, but let me just demonstrate how you would basically do that. Now it's running, as you can see here. It's got solved 0, solving 1, remaining 10, because we have it's 1 millimeter swept at 0.1 millimeter apart. Okay, so you're going to see eventually, let's see, when it solves 1, You gotta wait until source one, and then you start seeing the plots come out. You can also watch your convergence, so it hasn't even started yet, so still meshing. Okay, but that's what you get the idea. Okay, ladies and gentlemen, I appreciate you watching these. If you have any questions, you can always correspond, get back to me using either the this phone number. I operate out of Jordan, Jerash City. I go back and forth to the United States, but if you need any help with any of your design projects, if you need to outsource it, I could help you with that. Use basically designing anything from DC to 35 gigahertz. I appreciate your contact. And thank you very much. Have a good day.